Good day, everyone. So I'm going to discuss three examples, and these examples are representative of the whole of chapter 2 on bars. So here is the first example. For a bar shown, compute the nodal displacements and member forces. Also construct the actual load diagram. Compute the nodal displacements when the rightmost support is removed and a rightward force of 80 kilonewtons is acting. In both cases, modulus of elasticity is 200 gigapascals. So here is the figure, and take note that there are nodal forces already at node 2 and node 4. And first, we compute the stiffness of each individual stiffness of each member. So formula for stiffness is area modulus of elasticity divided by length. So for member 1, the area is pi radius 14 square times E 200,000 over length 1,200. So this is the value. For stiffness of member 2, area is pi 10 square, modulus elasticity 200,000 over length 1,000 mm. So the answer should be Newton per mm. Then stiffness of member 3, stiffness of member 4. Next is we determine the equivalent nodal forces. So we have this loading of member 2. So remember that the nodal force here, it should be rightward because the force or the nodal loads is rightward. So the effect is rightward. So this is equal to 120 W times length 1000 divided by 3 plus 360 times length 1000 divided by 6. So you'll get 100,000. On this and on the other hand, this is equal to 360 times 1000 divided by 3, then plus 120 times 1000 divided by 6. So you get 140,000. Then for this member here, member 3, we have in this joint or node, the equivalent load or force is equal to 300 Newton per mm times length 1500 mm divided by 3. So you get 150,000 rightward. On this side is 300 times 1500 divided by 6. So 75,000 newtons. Next is to compute for the net nodal forces. So let's begin with node 2. At node 2, this is the equivalent nodal force for the loading 100,000, but because there is already 16,000 at node 2, which is also rightward, so the net nodal force at node 2 is 100,000 plus 60,000 is 160,000 newtons. At node 3, we have 140,000. This is also at node 3, 150,000. So adding 140,000 plus 150,000 newtons is 290,000 newtons at node 3. At node 4, which is this, we have 75,000 rightward. Then because there's already a load here of 20,000 to the left, so minus 20,000, so we have 55,000 newtons at node 4. Next, we write the global stiffness matrix or the system stiffness matrix, or the other term is structural stiffness matrix. So let's number it 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I'll discuss first how to fill this up using the basic approach. Then also let's verify by our shortcut way. So we write the individual stiffness matrix, which is this one. This is K1, negative K1, negative K1, K1, and it is between 1 and 2, nodes 1 and 2. That's why we have row 1 and column 1, row 2, column 2. And for member 2, the stiffness is 62831, so positive, negative, negative, positive, and it is 2 to 3. Then member 3, 3 to 4, and member 4, 4 to 5. So for instance, this is row 1, column 1, and there's only one value here, row 1, column 1, 102,625.36. This is row 1, column 2. So row 1, column 2, negative 102,625.36. Then there is no 3, 1, if you look at here. There's no 4, 1, there's no 5, 1, so 0, 0, 0. Then remember that system stiffness matrix is symmetrical. So therefore, with respect to the diagonal, therefore we copy this row elements here with this column elements here. Then this is 2, 2. So we have 2, 2 here, 102,625.36. Then we have another 2, 2 here, row 2, column 2. So adding these two values, stiffnesses, you'll get 165,457.21. This is row 2, column 3. Row 2, this one, column 3. There's only this one. There's no other row 2, column 3. So we copy that value, negative 62,831.85. And that value is the same in row 3, column 2. 2, 3, K23 is equal to K32. So remember. Then this one is 4, 2. There's no 4, 2. Look at the numbering. There's no 5, 2 also, so 0, 0. Then we copy the elements in row 2 to column 2 by symmetry. Then this is 3, 3. So 3, 3 we have here 26,808.26. And another 3, 3 here, 62,831.85. So adding the two, we'll get 89,640.11. Then next, this one is row 3, column 4. So let's find row 3, column 4. This is it. There's only one. So that's the value here. There. Then 5, 3. There's no row 3, column 5. There's no row 3, column 5. So that's 0. Then we copy the values in this row 3 to also same values in column 3. And this is 4, 4. So 4, 4 here, 26,808.26 plus another 4, 4, 12566.37, you'll get 39,374.63. Then here, this is row 4, column 5. Row 4, column 5, there's only one. Row 4, column 5, negative 12,566.37. Then we copy all elements in row 4 to column 4. Then finally, this is 5, 5, and 5, 5 is 12566.37. So that's the basic. Then the shortcut is we just fill in the upper triangular matrix, and remember by symmetry, so we can easily fill in the rest. So remember that the shortcut to this is the first cell here, 1, 1 is K1, and this is K1 plus K2. So you add these two stiffnesses, that's the value. This is the negative of K1, that's the negative of K1, and remember. Then this is the sum of K2 and K3. So 62,831.55 and 26,808.26 is 89,640.11. And this is the negative of K2, the negative of K2, and remember. And the rest 0, 0, 0, 0, 0. Next, this is K3 plus K4. So this stiffness plus that stiffness is equal to this. And this is the negative of K3. So negative of K3. Then that is 0. Then finally, this is K4 plus K5. But there's no K5, so this is just K4. So K4 is 12,566.37, and the upper value is the negative of K4. This is also the negative of K4. So that's the shortcut way of writing the global stiffness matrix. And after that, we we substitute the value of these nodal forces into this system structural stiffness matrix with the forces. So F2 is 160,000, F3 is 290,000 newtons, F4 is 55,000 newtons. Then we have the displacements here, U1 up to U5. We know that there are no displacements at 1 and 5, so we eliminate rows and columns associated with zero displacements. Anyway, they are zeros. So we cancel this, leaving it from 5 by 5, it reduces to 3 by 3 matrix, which can be done by our calculator. So if we solve for U2, U3, U4, so we have F2, F3, F4 equals this reduced thickness times this displacement matrix. Therefore, the displacement matrix is equal to F2, F3, F4 matrix divided by this thickness matrix, but division means inverting that matrix. So therefore, U2, U3, U4 is the inverse of this reduced thickness matrix, which is 3 by 3. We copy the elements times the force matrix, which is 160,000, 290,000, and 55,000. So using our calculator, computing for the displacements, so U2, U3, U4 would be equal to 4.0688, 8.1680, and 6.9581 mm. After that, we solve for the global forces. So we copy this, P11, P21, and individual stiffness matrix of that element. Then the displacement multiplied by the displacement, which is 0, and U1 is, U2 is 4.0688, plus the fixed forces, since there are no fixed forces in member 1, so plus 0, 0. So computing this value by expansion, so 102,625.36 times 0 is 0, minus 102,625.36 times 4.60688, which is negative 417,562. Yeah, plus 0 is still negative 417,562. Then for the other force, P21 at the other end of number 1, so negative 102,625.36 times 0 is 0, then 102,625.36 times 4.0688, so positive 417,562 newtons. So to determine the end forces, or if the end forces are equal but opposite in signs, the type of stress that the member experiences is manifested by the sign of the second value. So it is in tension, because the meaning of negative 417,562 is leftward, and this is rightward at the other end, so the member will be stretched, so it is in tension. So again, the technique is, if the force T11 and T2 are the same but only in differ in signs, so you look at the sign of the second. So number 1 will be subjected to pure tensile force, so it is in tension. Next, for member 2, P22, P32, so this is the stiffness, the U2, then U3, then fixed forces, remember, negative 100,000 and negative 140,000 for the equivalent nodal forces. You can remember that. Now, they are negatives here because the fixed forces are always opposite to the equivalent nodal forces. If you can remember that equivalent nodal forces are rightward, because the effect of the loadings would be to stretch the member rightward. So the fixed forces would be leftward. So negative 100,000 and negative 140,000. So expanding 62,831.85 times 4.0688 minus 62,831.85 times 8.168 plus negative 100,000, you'll get negative 357,560. And for the second value, negative 62,831.85 times 4.0688 plus 62,831.85 times 8.168 minus 140,000, you'll get 117,560. So if this is member 2, at the left, the force is 357,560. At the right, 117,560. Number 2 is still in tension, but the force is not uniform because of if you can remember, member 2 is subjected to varying load. That's why the force change. Then for member 3, same process. You expand, then add the fixed forces if there are. So these are the opposite to the equivalent nodal forces of member 3. So you'll get negative 117,560 leftward. Then on the other side, it's also leftward. So for this member here, this is subjected to a portion of it is subjected to tension, then another portion of that will be in compression. Because member 3 is subjected to varying non-nodal forces. Then this is member 4. Then this is U4 and this is U5, 0 because this is fixed. And there are no fixed forces in member 4 if you look at the original figure in drawing. So there's none. So expanding, you'll get 87,438 and negative 87,438. So this is rightward and this is leftward. So member 4 is in compression. Then we now construct the axial force diagram, and you have two options here. You will make positive as tension, and you can also make it negative as tension, whichever you like. But if you consider positive force as tension, then this will be the axial force diagram. First, member 1 is subjected to 417,562 Newton force, and member 1 is in tension. Then this is member 2, 357,560 at the left, tension, and 117,000 at the right. So it varies. Look at the diagram. Then member 3, there's a portion that is in tension and there's a portion which is in compression. Look at that diagram there. So there's a portion where there is no force, axial force. So it crosses there. Then this is member 4. At the left, rightward, 87,438 and at the right, negative. But here it's negative because compression means negative. But if you use axial force diagram and you consider tension as negative, or if you base it from the original result, remember that at the left it's negative and at the right it's rightward, positive. So therefore the member 1 is negative 417,562. Then you have here negative 357,560 up to 117,560. Then next is 117,560 to 107,435. So negative tension, so it is now in compression. Then we have 87,438 newtons in compression. So in this case, because negative is treated tension and positive is treated compression, it is just the reflection of this axial force diagram. So I accept any axial force diagram as long as you specify if you consider positive as tension or negative as compression. So that's it. Then when the right the second question, when the rightmost support is removed and F5 is 80,000, so we can only eliminate one row and column associated with zero displacement. So the general stiffness matrix is now 4 by 4 matrix. And because 4 by 4 matrix is long, it requires time to invert it. So for situations where the the square matrix is greater than 3 by 3, because you can still use your calculator if it is 3 by 3 or 2 by 2. For more than 3 by 3 square matrix, like for instance this case 4 by 4, then I will allow you to use Excel to invert it or multiply the inverse and the force matrix. So this is now the new force matrix, 160,000 as before at F2, 290,000 at node 3, 55,000 at node 4, then 80,000 at node 5, which is the condition here. So to solve for the nodal displacements, we multiply the inverse of this 4 by 4 matrix to the force matrix, and using Excel, so look at the square matrix here, and this is the force matrix here. So in column AC, 4 cells, this is equal to, so we set up a function, this is equal to the product, the matrix multiplication of the first entry should be the inverse of this 4 by 4 matrix, inverse, from x1 to a4, aa4, and this matrix here, which is the first matrix, ab1 to ab4. And press shift control shift, hold down control shift, then press enter, and you will get these values here. So U2, U3, U4 will be equal to 5.70035. U3 is 12.4644, 17.5002 U4, and U5 23.8664. All these units will be in mm. So that's it for a case where you encounter 4 by 4, 5 by 5, especially trusses later. Then you should use Excel to get the product of the inverse of a matrix and another matrix, conformal matrix. Next, we proceed to this second example. For the bar shown, node 3 displaces 3.6. This is node 3 where there is an unknown force P to the right. Then determine the value of P, the nodal displacements, and the member forces. E is 169 gigapascals. Though in some cases, even if in the problem the unknown force is directed rightward, if the result gives us a negative value, it means that that force should be applied to the left. That is if you encounter a situation like that. So first step, we compute the individual stiffness. You already know that area E over length. So the area is pi 10 square. The modulus of elasticity is 169,000 megapascals, that is gigapascals, divided by length of member 900. So you'll get this stiffness. So I will not discuss this anymore. You know how to compute the stiffnesses. Next, the equivalent nodal forces for member 1. So this is supposedly K or W, 150 times length 900 divided by 6 from the unloaded end, 0 end. And at the right side, so you get 22,500 newtons rightward, because these are all rightward. but the fixed forces would be leftward. This is 150 times 900 divided by 3, so you get 45,000 newtons. Then for this member here, member 2, since this is uniform, actually uniform load, so this is just half of the area, or 150 newton per mm times half of 750, 350, because the other half is transferred to the right. So 150 newton per mm times 750 divided by 2 is 101,250. Therefore, the nodal force here, or the equivalent nodal force here, is P plus the equivalent nodal load there is 56,250, or 56,250 is 375, half of 750 times 150 plus 45,000, because there is 45,000 here, which is this. So you'll get 1,250 at node 2. Then at node 3, because 150 Newton per mm times 375 is equal to 56,250, and there is a force P there already active. So the net nodal force at node 3 is P plus 56,250 newtons. Then at node 4, of course, it's obvious, it is negative 30,000 newtons. Then we will solve the nodal displacements into 3 ways, 3 techniques. So I'll present all the 3 here. First, the easiest one is by observing that from this general stiffness matrix, I hope that you know already how to set this up. This is only 4x4. So these are the forces. At node 1, we have F1 plus 22,500. Take note of that because there is 22,500 acting to the right there. At node 2, 101,250. Node 3, P plus 56,250. And at node 4, negative 30,000 newtons. Then this stiffness multiplied by this force matrix is equal to this stiffness here, system matrix, multiplied by the global displacements. And we eliminate rows and columns associated with 0 displacements. So after that, it leads to a 3x3 matrix. However, there is an unknown P here, so we cannot simply solve for U2, U4, and of course this is given 3.6 by inverting this and multiply it by this. So the technique is, if you notice, if we expand row 2, luckily this is 0. So if we expand row 2, 101,250 equals this stiffness times 0, so that's still 0, plus this stiffness times U2, plus this stiffness times 3.6, plus 0 times U4, then we can compute U2. Same is so if we expand row 4, because there's a value here, so 0 times 0 plus 0 U2, so that's still 0, unknown. Then negative 28,316.22 times 3.6, you can get the value, plus 28,316.22 U4, then we can solve U4. So that is, first we expand row 2 to solve for U2, then expand row 4 to solve for U4. Then having found U2 and U4, after we expand this, and we expand row 2 to solve for P. So when we expand row 2, this is 101,250 equals 169,602.37 times U2. then minus 11,06110.24 times 3.6 plus 0 times U4. So solving this equation, you'll get U2 equals 2.9448 mm. Then expand row 4, negative 30,000 equals 0, 0, U2. Then negative 28316.22 times 3.6 plus 28316.22 times U4. So that's the equation after we expand row 4. There is only one unknown here, U4, so we can solve U4 2.5405 mm. Then after that, we expand row 3 because we already know U2 and U4. So expanding U3, so we have P plus 56250 equals negative 11,0610.24 times U2, which is 2.9448 plus this stiffness times 3.6, then minus 28316.22 times U4, and we already know U4. So that's why we get P equals 46,223 newtons. Now, you may encounter a situation which is a little bit not complicated, but it will just involve two equations to unknowns. Unlike here where we have computed directly U2 and U4, but you may experience a problem where after you expand there will be two unknowns or even three unknowns. So there's no problem there because if there are three unknowns in its expansion, let us say there are so many, the size of the matrix is large. However, you can still manage to solve for U2, U3, U4 after expansion if it involves three unknowns. So there's no problem as long as the number of unknowns after you expand the rows will be three or less. So that is still manageable. Unless it is still more than 3, so 4, and you use Excel for that system of equations or matrix. So we already answered the force P, then the nodal displacements U2 and U4. So before we solve for the member forces, though the nodal displacements have been found, let me discuss first other techniques to solve for the global displacements. The next technique is by the numerical methods technique, which states that if displacement is specified at or introduced at coordinate n, then replace the cell or the stiffness of that nn, in this case node 3, because P is at node 3 and 3.6 is specified at node 3, so replace K33, the stiffness of K33 by the stiffness of that matrix multiplied by a very large value. So how large? So I suggest that that large value is 10 to the 10 or 1 times 10 to the 10. You can make it 1 times 10 to the 20 if you want, but that's enough. This is already sufficiently large, 1 times 10 to the 10. So the original stiffness of 33 was 138,926.46. It is at the same row as this unknown B here. So this is 33. So multiply this by 1 times 10 to the 10. It becomes 1.3892646 supposedly, but I stopped to 3. It will not fit in this cell. Times 10 to the 15. And the force value of that row by this cell here, which is 1.3893 times 10 to the 15 times the specified displacement. So you have to replace the first value here by the specified displacement times the value here after we multiply by a very large value. So since this is already KNN times L, all you have to do is replace the first value here, which is P plus 56 to 50, by this value. And this value is obtained by multiplying this further, this cell here, or this stiffness here, which is very large, by 3.6. And that becomes 5.00135 times 10 to the 50. So, since this is only 3 by 3, then U2, U3, U4 is equal to the inverse of this matrix, 3 by 3, times this new force matrix. So that is U2, U3, U4 is equal to the inverse of this matrix. Take note of this stiffness here, which is now large. So inverse times this new force matrix. So 102, 101 to 50, and 5.00135 times 10 to the 15, times then negative 30,000. Using your calculator, you can invert the 3 by 3 matrix with your calculator. You can multiply two matrices also. Then you'll get U2, U3, U4, which is equal to 2.94475. This is almost the same as that. Then 3.6, this is practically 3.6, which is the specified displacement. Then 2.54044, which is most likely same as that practically. So that's the second technique. The third technique is by partitioning. So if you can remember, I give you a problem on getting the product of two matrices by partitioning technique. So that's the purpose of that. So this is the original matrix. Now, before you partition, you cannot use this directly. So the suggestion is you put all the known displacements at the last row, and in the upper rows, the rows where the displacements are not known or to be determined. So in this case, we do not know U2, we do not know U4. So we change the numbering, therefore, because this should be the row where displacement of 2 is found. Then next is U4 or row 4. So 2, 4, then the known displacements. For instance, row 1 has known displacement 0. Then row 3 has known displacement 3.6. So this is the arrangement. So 2, or because U2 is unknown, 4, because U4 is unknown, then knowns at the last. So we know U1 is 0 and U3 is 3.6 specific. So therefore, the numbering will also change. So 2, 4, 1, 3. So 2, 4, 1, 3. And this is how we partition it. Take note that the force matrix would be known forces at the upper rows, unknown displacements at the upper rows, then unknown forces at the bottom rows, but known displacements at the bottom rows. Now, because the numbering is changed, the value or the entries here will also change. So this is 2, 2. So all you have to do is grab 2, 2 here. 2, 2 is 169602.37. So this is it. Then this is 4, 4. 4, 4. 28316.22. 1, 1. So 1, 1. 58. 992.13. And this is 3, 3. 3, 3. 138926.46. Then for the other cells, this is row 2, column 4. Row 2, column 4 is 0, so that's why it's 0. 2, 4 is also 0. Still, this is symmetrical. Then this is row 2, column 1, row 2, row 2, column 1, negative 58,992. So that's why we have negative 58,992.13. Same is to with row column 2, row 1, column 2, row 1, which is this. So they are equal. Then this is row 2, column 3, row 2, column 3, negative 11, 0610.24. Which is that. Then this is row 4, column 3, 4, column 3, row 4, column 3, this one, negative 28,316.22. Then row 3, column 4, row 3, column 4, row 3, column 4, this one. So that's why they are equal. And so on and so forth. So I hope you know how to transfer values here. Remember, they are also symmetrical. That's it. Just look at the numbering. Then I will call this square matrix KPP in general. Then this one is KPS, this 2 by 2 matrix. This 2 by 2 matrix below the partitioning is KSP, and this is called KSS. So let's uh, generalize the equation by expanding. This is the third way technique. So we reorder the rows and columns in such a manner that the unknown displacements are in the upper rows and the known displacements in the bottom or lower rows. So this is the partitioning in general. Remember, this is KPP, KPS, KSP, KSS. Then you have UP and U sub S. So using by expansion of the matrices, then we have FP. This is equal to FP. It is equal to this square matrix KPP times U sub P plus KPS times U sub S. Now, if US is 0, if this is 0, then this second term will be 0, and the result will be FP equals KPP times UP. This is very easy because U sub P is simply the inverse of KPP times the force matrix. These are known forces. And this is the same procedure and results as deleting rows and columns associated with zero displacement when U sub S is 0. When this is 0, remember, you can solve for the unknown displacements directly. It is the inverse of this matrix times this force matrix, which is known. So that is the same. But when US is not entirely 0, or some of these uh, displacements are given, that's like in this problem. So one is 0 and the other is given 3.6. Then we are forced to solve for U sub P because this is known. We can evaluate the value of this. So after we transpose this to the left, then we have force matrix which are known minus this value which can be calculated is equal to KPP UP. Therefore, if you solve for U sub P, it is equal to the inverse of this matrix times this force matrix which is known minus this value, the product of this stiffness and this displacement matrix, which can be computed because US are known values. So if then you can simplify this. This will give us one force matrix, column matrix specifically. Then we can solve for U sub B. So we will demonstrate that here. So U to U4 therefore is equal to KPP. This is our KPP. This is it. Then inverse of this KPP multiplied by the force matrix 102, 250, and negative 30,000 minus this matrix here, KPS, this is KPS, times this US here. So remember how to expand or get the product of two matrices. So we can simplify this value. So we have negative 58,912.13 times 0, it's still 0. Then negative 110610.24 times 3.6 is negative times negative, so positive 101,250 plus 110,610.24 times 3.6 will give us this value here. Then for the second part, 0, then this is negative 28,316.22 times negative, so positive, negative 30,000 times the positive value of this product is 71,938.32. Then you can use your calculator to get this product of the inverse of this 2 by 2 matrix and this 2 by 1 matrix. The result would be the same. U2 is 2.94481 and U4 is 2.5405 for ml. Finally, we solved for F1 and FP. So remember, F1 is F1 plus 22,500, not really F1, but there is a force there due to the non-nodal forces equivalent to the triangle there. So we expand row 1, this is row 1 actually. So negative 58,992.13, then 0, negative, this matrix here multiplied by U2, U4, this one, U2, U4, plus this matrix here multiplied by 0, 3, 6. So if we simplify this product, the result is this. And if you simplify this product here, this is the result. So that F1 is negative 173,720.614 minus 22,500. So you will get negative 196,221. And the value of P is negative 397,664.63 plus 500,135.256 minus 56,250. So this is 56,250. So you'll get F1 equals negative 196,221 and P is 46,221, which is almost the same as before, 46,220. Then for the member forces, because this is the last technique, this is stiffness of member 1. U1 is 0, then this is U2, and these are the fixed forces opposite to the forces, nodal forces. Then you'll get this member force member 1. Then for member 2, stiffness of member 2, this is U2 and U3 specified. Fixed forces of member 2 is the same because it was rectangular loading. Then you'll get these values. Then number 3, U3, U4. Then there's no fixed forces for member 4. There was no load. Then here, there's no load. Then you'll get 30,000, negative 30,000. Which is this one, right? Negative 30,000. Then let's check the equilibrium. So this is 196,200. 196.221 kilonewton. Let's convert that to kilonewtons. So it is leftward because this is negative. The equivalent loading here is the area of this loading diagram, 1/2 of 900 mm times 150. Then let's convert that to kilonewton, divided by 1000, so 67.5 kilonewtons. This is 150 newton per mm times 750 mm. Then that will be 112,500 newtons divided by 1000, so 112.5 kilonewtons. The value of P is 46.221 kilonewton. And we have 30 kilonewton here. So check summation forces X equals 0. So you get negative 196,221 plus 67.5 plus 112.5 plus 46.221 minus 30 equals 0. So that checks the value. So finally, our example 3 involves temperature changes. So this is the problem. We have non-nodal loadings or forces, and we have nodal forces already. The areas are known. So for the stiffnesses, I will not anymore discuss in more detail about this. You know this already. These are the stiffnesses. Then let me discuss first how to compute the fixed forces due to thermal effects. Remember that the deformation due to stress or load is just equated to the thermal displacement or elongation or contraction. So this is the formula: force length over AA. Then for thermal expansion, beta L delta T or balat. So cancel out L, then solve for P. P therefore is beta delta T AE. So the fixed force therefore for thermal changes would be beta delta T AE. Then we multiply this by 1 negative 1. By the way, that's the equivalent force at the left and at the right. Delta T would be positive if the change is increasing, and it is negative if it is decreasing. So this is the fixed forces for thermal effect. Then remember that the nodal forces are opposite to the fixed forces. So let's make this as our base. Then remember that we just change the direction for the equivalent fixed nodal forces. So how to compute the equivalent nodal forces? So remember, they are opposite to the fixed forces, and this is the formula for fixed forces. So fixed forces in member 1. So beta is given 13.6 times 10 to the negative 6. Change in temperature is positive 50 because we have temperature increase for members 1 and 3. Then length of area of member 1 ladder is 600 mm square. Then modulus of elasticity 180,000 megapascals times 1 over negative 1. So we have 73,440 and negative 73,440. So the fixed forces is at the left side of member 1 rightward and at the right side of member 1 leftward. But the equivalent nodal forces would be opposite. So if it is rightward, the nodal equivalent force would be leftward. So you have here 73,440 equivalent nodal force leftward, opposite to this 73,440, which is rightward. On the other end, because this is negative, supposedly the fixed force is leftward. So that's why the equivalent nodal force due to thermal effect is rightward, 73,440. Then for the nodal force for this member, this is rightward. So it is just half of the area. 200 times 500 is 100,000 newtons. So rightward. There's no problem with this because we already mastered this, how to compute the equivalent nodal force. Then on the other side also, it's 100,000 rightward at this node 2 here. But because there is already 75,000 newtons rightward, so we also put 75,000 newtons. So these are the nodal forces at node 1, node 2, node 3, node 4. So for node 2, I already discussed that. So let's proceed to node 3. Member 3 is subjected to thermal increase of 50 degrees Celsius. So let's compute the fixed forces for member 3. So area is 400 and E is 180,000 times 1 over negative 1. So positive 48,960 newtons fixed force due to thermal effect, and negative 48,960 newtons due to thermal effect. So fixed forces rightward at left, then leftward at right. But the nodal force is opposite to this. So if this is rightward, then equivalent nodal force should be leftward. So leftward 48,960. Then the equivalent nodal force due to this loading is 240 times 1,200 over 3. That's why you get 96,000. That's rightward. There is a load of 120,000 to the left, so we put it there, negative 120,000 leftward. Then at node 4, we have this is leftward, so the equivalent nodal force is rightward. So that's why you have rightward there, 48,960. Then, of course, due to this loading here, this is 240 times 1,200 over 6, so 48,000. So these are only the forces. Then at node 5, no nodal force. At node 1, although there are nodal forces, but this is a fixed and this force cannot produce stress in this fixed wall here. So, or in other words, the wall remains undisplaced or unyielding. It will not displace, so zero displacement. We can still cancel that later. So what is important? What are important nodes are 2, 3, and 4, because 1 and 5 have zero displacements. So what are the net nodal forces at these nodes? So we study here. So we have 73,440 plus 100,000 plus 75,000. Add all this because they are all to the right. So we have also to the right here 248,440. The equivalent nodal force at node 1 is 100,000 minus 73,440. So 26,560 rightward. At node 3, we have 96,000 minus 48,960 minus 120,000 is negative 72,960 or 72,960 leftward. Then at node 4, we have all nodal forces rightward. So 48,960 plus 48,000, 96,960 newtons rightward. So we now have nodal forces at 2, 3, and 4. We can now evaluate the nodal displacements. So we have F1, not important because the displacement is 0. Node 2, node 3, node 4. Then you know already how to fill this system matrix or system of bars. I will not explain that anymore. Anyway, we have here the stiffnesses, individual stiffnesses. So the 5 by 5 matrix again is reduced to 3 by 3. So we can solve U3, U4, U2, U3, and U4. So this is equal to the inverse of this reduced 3 by 3 matrix times this force matrix here. So U2, U3, U4 is equal to this matrix, its inverse, which you can do by your calculator, times this column matrix of the forces here. So using your calculator, you'll get U2, U3, U4 1.999604, 1.67880, 2.353426 mm. For the member forces, stiffness of member 1, times the displacement 0 and u1, u2. u1 is 0, this is u2, plus fixed and forces. So fixed and forces, we have, of course, uh, fixed and forces, these are nodal forces. So the fixed and forces would be 73,440, then minus 100,000, opposite to this. So 73,440 would be treated positive, then 100,000 would be treated negative. Or in other words, because this is rightward nodal force, you just change the sign, so leftward. So we have here negative 26,560. Then for the other end, do not use negative 248,440 because 75,000 Newton is not an effect, is not a fixed end force. It is an applied force already. So the fixed end force or forces will be only 73,440 due to temperature, and this is due to that load. So because these two are rightward, the fixed end force will be leftward. So negative 100,000 and negative 73,440 is negative 173,440. So solving for P1 and for the forces of member 1, you just expand this matrix plus this matrix here. You get negative 242,517, and for 2, 42,517 newtons. And for member 2, this is member 2. There are no forces here, and member 2 is also not subjected to thermal changes. So there will be 0 fixed forces for member 2. So this is the stiffness of member 2, then this is U2 and U3. So expanding, you'll get 32481 and negative 32481 newtons for the left and the right forces of member 2. So member 2 is subjected to compression because this is rightward and this is leftward, so the member 2 is in compression and it is uniformly compressed, unlike the other members. Members 1 and 3 are not uniformly stressed, or yes, not uniformly stressed. Then for member force 3, this is the stiffness of member 3, 60,000, negative 60,000. Then this is U3 and this is U4. U3, U4. The fixed forces for member 3 are disregard 120,000. So we have positive 48,060 opposite to this, so positive minus 96,000. So 48,960 minus 96,000 is negative 47,040. And on the other end, these are all rightward, so the fixed forces will be leftward. Negative 48,960 and negative 48,000 is negative 96,060. So perform the multiplication of these two matrix, then add negative 47,040. So you'll get negative 87,518. And in the second row, it is negative 56,482 newtons. And lastly, for the member force of member 4, fixed forces would be 0. Stiffness, then U4, U5, 0. So you get 56,482, then negative 56,482. So member 4 is subjected to compression because it's negative. And it is uniformly compressed. So that's all. I hope that these 3 examples are enough to cover the entire chapter 3.